Hello and welcome to this look at an applied KP exam question on a process that's often employed after the Haber process has been used to make some ammonia in the chemical industry. This is called the Ostwald process, and you don't need to know about the Ostwald process, but it's used to make something called nitrogen 2 oxide, sometimes known as nitrogen monoxide. Excuse me. So it gives you some information about the Ostwald process, and what we're going to focus on is how to calculate the value for Kp. So the way to do this is to take the equation and create an ice table. The number of moles at the start is the initial moles. The number of moles that each one changes by is the C, and then the number of moles at equilibrium is the E, hence the ice method, ICE. So looking at the data they've given us, you can put the numbers in where relevant, and you can assume that at the start there is no nitrogen 2 oxide and there is no steam. However, you're told that at equilibrium you have 100 moles of nitrogen 2 oxide. So if we take a closer look at the mole ratio, you can see that there are 4 moles of NO. So your 100 is going to be something multiplied by 4, which would be 25 obviously. So applying that across the board to my reactants and my products, I can now work out what the number of moles at equilibrium are for everything. So adding up those moles enables us to work out the mole fraction and the partial pressure. So the mole fraction was obtained by, I'll go through one of them with you, 100 over 825 gives you 0.12. 475 over 825 gives you 0.578. And again, 100 over 825 gives you 0.12. And then 0.18 is derived from 150 over 825. So the mole fraction should roughly add up to 1, and the partial pressure should add up to the complete pressure, the total pressure. So our total pressure is 500 kilopascals. So these partial pressures were obtained by multiplying these mole fractions by 500 in each case. So these numbers should roughly add up to around 500, or as close to you as you can get. If you did a bit of rounding, for example, as you went, it might be slightly more or slightly less. So what's interesting about our Kp expression is it's got quite a lot of coefficients in it. It's not seen very often. That's because you have quite a lot of large mole ratios, 4, 5, 4, and 6. So these need to go in as coefficients or powers by which you multiply up the partial pressures. So putting in the numbers, you end up with an expression that looks something like that. And tapping those into a calculator gives you this, which then gives you 0.285546875. Now they want you to give your answer to an appropriate number of significant figures. So looking at the numbers, everything is to 3 sig figs. So I'm going to change that to 3 sig figs and express it as 0.286. Now the kilopascals came from the cancelling through. Obviously there's down to the power of 18 there. So if we have a quick look here, you have 10 partial pressure terms on the top and 9 partial pressure terms on the bottom. So it doesn't take too much to work out that by cancelling that through, that'll give you kilopascals as the units. Okay, I hope this has been a useful look at a slightly more applied example. Until next time, thanks for listening and see you soon.